Students, in this video, we will discuss second form of Taylor's theorem and then Mclaren's theorem. And then we will take one example. Fine. So second form of Taylor's theorem. This is an alternate form. Basically, we have this as the Taylor's theorem. This is which we have already proved in the last class. So now if this is valid in the interval a to a plus h. But if your interval is very large, suppose a to x for example, then how to transform this expansion in that interval? This is the problem. So that's why we are having second form. So if f satisfies the condition of Taylor's theorem in a to a plus h, conditions are, these are the conditions: n minus 1th derivative of f is continuous on this interval, nth derivative of this exists in the open interval, then there exists a theta. So these conditions are satisfied. Fine. So here, so if f satisfies the conditions of Taylor's theorem in this interval and x is any point of a to a plus h, then it satisfies the conditions in the interval a to x also. X is any point in this, so that is also satisfied the conditions in this interval, subinterval. Basically this is the subset of this. So now our aim is to extend or expand the function in this interval. So now here replace a plus h by x. So that's why h is equal to x minus a. This is equal to h, x के बराबर रखेंगे, so h की वैल्यू आ जाएगी x minus a in Taylor's theorem expansion. So we get, this is the Taylor series expansion. This is the Taylor series expansion, original one. And then replace this a plus h by x minus a. Sorry, x. And h is replaced by x minus a. So we get f of x is equal to f of a. From here h is x minus a. So x minus a f dash a. From here x minus a whole square divided by factorial to a second derivative and so on. Second last term is here, x minus a raised to the power n minus 1 divided by factorial n, and this plus this term. So x minus a raised to the power n 1 minus theta raised to the power n minus p divided by p n minus 1 factorial, and nth derivative at a plus theta, and h is x minus a, where theta is in between 0 and. So this is basically the expansion. This is the second form of Taylor's theory. And this last term is basically known as the remainder term. So this is known as the remainder term after n and denoted by Rn. Now if you put a is equal to 0 here in star, what is the star? Star is this equation is star. So put a is equal to 0 here. So here we have f0, fx, f dash 0, x square by factorial 2, second derivative at 0, x raised to the power n minus 1 divided by n minus 1 factorial, n minus 1th derivative of f at 0, and similarly here. So this will be nothing but the, so after putting a is equals to 0 we get this expansion in star. Fine. And this is basically nothing but the Mclaren's theorem. तो ये जो आया है ये Mclaren's theorem है, एक्चुअली Mclaren's theorem से ये डेवलप हुआ है. Fine. So now Mclaren's theorem. So we are proving this separately here. So if a function f defined on the interval 0 to x, because a is 0 here, so that's why this quantity is 0. So 0 to x is such that the n minus 1th derivative of f denoted by this is continuous on the interval 0 to x. The nth derivative of f denoted by this exists on the open interval 0 to x. P belongs to n, natural numbers. Then there exists a real number theta in the open interval 0 to 1 such that f of x is equal to f of 0 plus x f dash 0 plus x square by factorial 2 second derivative at 0 and so on, and x raised to the power n minus 1 divided by n minus 1 factorial, and n minus 1th derivative of x as 0 plus x raised to the power n 1 minus theta raised to the power n minus p divided by p into n minus 1 factorial and nth derivative at theta x. If you will see, both are same. So this is actually the Mclaren's theorem. So this and this both are same. Now we want to prove this separately. So if you remember the Lagrange's, so we are using the same concept here. So consider the function phi at t is equal to ft plus x minus t f dash t plus x minus t whole square by factorial to second derivative at t and so on, x minus t raised to the power n minus 1 divided by n minus 1 factorial, n minus 1th derivative of f at t plus some a x minus t raised to the power p. So this is as it is same as we have taken in the Lagrange's theorem. Here, if you will see in Lagrange's theorem, here we have taken the same. In Lagrange's theorem we have taken this. So a plus h is replaced by x. So here is h is replaced by x minus a whole square by 2 and so on. And a is substituted as t. A is substituted as t. So this is the assumption. Fine. So here we have taken this. This is our initial phi. So now here is p. So now where a is a constant to be determined such that phi of 0 initial point is equals to phi at x end point. दोनों पे वैल्यू सेम होनी चाहिए, लेफ्ट पे भी और राइट एंड पे भी. So from this, now if you put x here, put phi at x is equal t is equal to x right hand side, this right hand side. So what you will get? You will get f of x plus 0 due to this factor x minus x will be 0, 0, 0, 0. So ultimately f of x. So I am writing this. This is basically phi of x. Phi of x is f of x is equals to, now phi of 0. Put t is equal to 0 here. So f of 0 plus x f dash 0 plus x square by factorial 2 second derivative at 0. So we are getting these terms up to here, x raised to the power n minus 1 factorial n minus 1 derivative at t, so t will be 0, plus from here a x raised to the power p. This is equation number 1. Now our aim is to find out this a. So a is evaluated. Now since number 1 f, f1, f2, n minus 1 they are all continuous, and x minus t raised to the power r belongs to n is also continuous. This is the last term of your assumption. Assumption का जो last term है वो ये है. So obviously since they are continuous, hence phi is also continuous in the interval. F, f1, f2, fn minus 1 are all derivable in the open interval 0 to x, and this term is also derivable, hence phi is also derivable. Third, phi of 0 is equal to phi of x. Then by Rolle's theorem there exists a theta in the interval 0 to 1 such that phi dash at c. अब c की जगह क्या हो गया हमारा? इंटरवल है ये. सो इंटरवल है हमारा 0 प्लस सम थीटा x. This is our basically c. This is our c where theta is in between 0 and 1. So c is in Rolle's theorem, c is nothing but 0 plus theta x. आप थीटा की वैल्यू यहाँ से वेरी करते रहिए, you will cover up all the interval from 0 to x. ठीक. So phi dash 0 plus theta x is equal to 0. That means phi dash theta x is equal to 0. This is equation number 2. Now since from star is this. This is our star. Phi dash, इसको डिफरेंशिएट करो. phi dash t is equal to f dash t plus यहाँ से करेंगे. So we get with respect to t, so we get minus f dash t. f dash t से f dash t कैंसिल आउट. फिर इसको एज इट इज रखेंगे, इसको डिफरेंशिएट करेंगे सेकंड डेरिवेटिव. ये टर्म नेक्स्ट टर्म के साथ कैंसिल हो जाएगी. अल्टीमेटली ऑल दीज टर्म्स विल बी कैंसिल आउट. केवल कौन सी बचेगी? एक यहाँ से आएगा एक टर्म. कौन सा टर्म आएगा? x माइनस टी रेस्ट टू द पावर n माइनस 1 डिवाइडेड बाय n माइनस 1 फैक्टोरियल एंड डेरिवेटिव ऑफ दिस n f n t. nth डेरिवेटिव बचेगा यहाँ पर और एक यहाँ से बचेगा. a p x minus t raised to the power p minus 1 and minus 1. तो ये हमारा लास्ट के दो टर्म बचेंगे. So we are taking here this. So this is the derivative of phi, second last term and last term. Now put t is equal to theta x. So this, and substitute this. So after substituting t as theta x, we get this. Now phi dash theta x is 0. So this is 0 is equal to this, and from here find out a. So a is equal to this, and now substitute this in star. So we get this expression. This is the Mclaren's theorem. So Mclaren's theorem, this. And last term is basically the remainder term. This is the remainder term Rn. So this is the remainder term. And again, this is known as Shilo-Milch and Rocci form of remainder. फिर वही, if p is equal to 1, we get this. If p is equal to 1, we get this expansion, which is known as Mclaren's theorem with Cauchy form of remainder. If p is equal to n, then we are getting this. इस p की वैल्यू एक बार 1 रखी, एक बार n रखी. This is known as Mclaren's theorem with Lagrange's form of remainder. So this is the Mclaren's theorem. Now take one example on Mclaren's theorem. So expanding the following by Mclaren's theorem with Lagrange's remainder. That means we are considering this Lagrange's form of remainder. So p should be n. So here p should be n because we are considering Lagrange's. So p should be n. And expansion is this. So our function is basically sin ax. ठीक, तो sin ax का expansion करना है. This f of x is sin ax. इसको expand करना है, so we get this. So let's see. So let f of x is sin ax, this function. Now we need derivatives, first derivative, second derivative, n minus 1th derivative. So first find out these derivatives. So first derivative is a cos ax. अब इसको हम जो है साइन में दोबारा कन्वर्ट करेंगे क्योंकि हमारा ओरिजिनल फंक्शन है साइन. सो जस्ट ऐड पाई बाय 2 हियर. सो a sin ax plus pi by 2. So again we have converted our cos in terms of sine. Second derivative, again differentiate this. We get a square cos ax plus pi by 2. Again convert this cos into sine. So a square sine ax plus 2 pi by 2. So now you can see that we are having a generalized formula. तो हमारे पास एक जनरल फॉर्मूला आ जाएगा. That third derivative is this. Again convert this into sine. So we get a cube sine ax plus 3 pi by 2. And so hence if you want to find out the n minus 1th derivative, then this will be a raised to the power n minus 1. Sorry, this will be n minus 1. A raised to the power n minus 1 sine ax plus n minus 1 pi. Here is third derivative, so we get 3. Here n minus 1, so n minus 1 pi by 2. And nth derivative will be an sine ax plus n pi by 2. Fine. Now put x is equal to theta x. X is equal to theta x, so an sine a theta x plus n pi by 2. Now we need the values, all these values at x is equal to 0 except the last one. So except the last one, बाकी सबकी सब 0 पे वैल्यू चाहिए. तो f0 is 0, f dash 0 is a sin pi by 2, which is a. Second derivative at 0 is a square sin 2 pi by 2, so a square into 0, so 0. So hence we can find out. And the n minus 1th derivative, this at 0 will be a n minus 1 sin n minus 1 pi by 2. Since we don't know n, so that's why left is this as it is. Now from the Mclaren's theorem with the Lagrange's form of remainder, this is the formula for the Lagrange's form of remainder. Put all these values. So f of x is sin ax, f0 is 0, 0 plus x f dash 0 is a, so a plus x square by factorial 2. Second derivative at 0 is 0, 0, x cube by factorial 3, we get minus a cube, this plus and so on, all the terms. Now the second last term will be here, this x n minus 1 divided by n minus 1 factorial, and n minus 1th derivative at 0 is this. So a n minus 1 sine n minus 1 pi by 2 plus, now the last term, this xn by factorial n and nth derivative at theta x. So nth derivative at theta x is this. So substitute it here. Fine. And now this is the final solution. If you simplify this, so ultimately this is the expansion. This is the required result. So this is the Mclaren's theorem. Fine. So now in the next class we will discuss about the some examples we will discuss. Fine. Thank you.